No, you shouldn't. That's okay. I'll delay for 30 seconds until we finish. All right, so let me go through the steps here. And again, it's going to be very difficult to capture all this in a two-dimensional form. And so as soon as I'm done with this, I'm going to actually show the video that shows this process again. And then we'll go back here again, and then we'll come back to the DVD. So you'll see it in motion and hear it, and it'll be a little more salient then. All right, so basically the first thing that happens in translation, basically, mRNA comes out of the cytoplasm, goes to the ribosome, basically. The ribosome's two pieces, it snaps on, grabs it, okay, bingo. And what happens is then the tRNA that's floating around out there with this, amino acid already stuck to it, has an opening. And that opening is an exposed codon that matches the corresponding anticodon, which follows those same complementary rules that we saw earlier. A to T, A to U, U to A, G to C, C to G, right? So if your codon says, again, U, the anticodon is going to say A. And that, you can go back to the genetic code, that chart, and you can basically say, oh, well that tRNA is going to bring in asparagine, whatever it happens to be the name of that corresponding amino acid. And that's how the sequence of DNA can determine the sequence of amino acids and therefore what the protein's going to be like. So going from DNA to mRNA to tRNA preserves that order and type of amino acid. Okay? All right. So that's the first step. There are two sites on the ribosome. There's a first step and a second step. You'll see this again in a second. So one step gets filled. The ribosome moves on down the chain, exposes another site. Another tRNA comes along. Second tRNA transfers the amino acid to the chain. And it takes energy to do that, by the way, ATP to do that. So to make proteins, it costs energy. And by doing that, by forming two amino acids together, you form what's called a peptide bond. And thus the name polypeptide, the bonds between amino acids. And this process continues from the start signal to the stop signal until the gene is coded. Okay? At which point the ribosome falls apart. You have a big long strand of amino acids / polypeptide that goes wherever. It may go to Golgi for further processing, to be pieced together, to be formed into a package to be exported. It may go somewhere to help part of the cellular respiration. Who knows? All right. So that's a big picture. Okay. Sorry. I don't blame you. It wasn't in your head. And your book does a really good job, by the way, of this part. The translation, there's a 2-page depiction of this process, and I have to say this is one part we'll actually say the book had some nice pictures and did a good job of it. So if you haven't read that part yet, actually do. Okay, I'm going to come back and recap these steps after we watch the actual motions, so don't panic if you didn't get it all. Okay, now, because I'm 51 years old and forget sometimes I get bored watching the same videos, so I change it up between classes. Is this the same one we watched yesterday, or is this a different one? I want to give you a different one. I think it's the right one.
This is the one we watched yesterday.
You watched this one? All right, so then let me change it up. All right.
What you are about to see is DNA's most extraordinary secret. The innermost workings of how a simple code is turned into flesh and blood. This is what Francis Crick called the central dogma of modern biology. how DNA makes protein. It starts with a bundle of factors assembling at the start of a gene. It's these that trigger the first phase of the process, reading off the information that will be needed to make the protein. The gene is the length of DNA stretching away to the left. Everything's ready to roll. 3, 2, 1.
What do you think
The
that guy
blue
is?
molecule racing along the DNA is reading the gene.
The TR.
It's unzipping the double helix
RNA
and
polymerase.
copying one of the 2 strands.
These are all the nucleotides out there.
The yellow chain snaking out of the top is a copy of the genetic message,
mRNA.
and it's made of a close chemical cousin of DNA called RNA. The building blocks to make the RNA enter through an intake hole. They are matched to the DNA, letter by letter, to make an exact copy of the A's, C's, G's, and T's of the gene. The only difference is that in the RNA copy, the letter T is replaced with a closely related nucleic acid known as U. You are watching this process, called transcription, in real time. It's happening right now in almost every cell in your body.
Isn't that amazingly fast?
It's a bit like taking the information off a hard disk on a computer and put it into memory, but making it a real program that's running. So that process of DNA to RNA is like running a program, double clicking on an icon.
When the RNA copy is complete, it snakes away from the nucleus and into the outer part of the cell.
That's the nucleus.
Then, in a dazzling display of choreography, all the components of another molecular machine lock together around the RNA to form a miniature factory called a ribosome.
Ribosome.
It translates the genetic information in the RNA into a string of amino acids that will become a protein.
These are the tRNAs out here.
Special transfer molecules, the green triangles, bring each amino acid to the ribosome. The amino acids are the small red tips attached to the transfer molecules. There are different transfer molecules for each of the 20 amino acids.
Those are all different.
They all
amino acids.
carry a specific 3-letter code that will be read by the machine. Now we come to the heart of the process. Inside the ribosome, the RNA is pulled through like a tape. The code for each amino acid is read off, 3 letters at a time, and matched to 3 corresponding letters on the transfer molecule.
And that's right here. So this is the codon from the mRNA, and here comes the tRNA that has a corresponding anticodon. And it's a real brief thing. It goes bing, boom, goes off the DNA, bing, boom. Comes in, transfers this amino acid, gets the heck out of there. Okay?
When the right transfer molecule plugs in, the amino acid it carries is added to the growing protein chain. Again, you are watching this in real time. And after a few seconds, the assembled protein starts to emerge from the ribosome. Ribosomes can make any kind of protein. It just depends what genetic message you feed in on the RNA. In this case, the end product is hemoglobin.
So we're basically some machine. The ribosome is a machine. Sorry about that. And it works based on the code coming in. It's like a tape. Comes in, reads it off, brings in, bing, bang, boom, transfers it, and just translates that coded message and the codons of mRNA into basically a protein, a polypeptide. Okay, and that's what it's all about. Yes?
So based on the code that comes in, it decides which protein that is, and it pushes that out.
It determines what protein is. Yeah, the gene the sequence of DNA creates a transcribed message of mRNA that's translated into the protein that was coded for on that DNA. So that's the link. Okay? Now, I'm going to show this one more video other than this.
A transfer RNA molecule is composed of 70 nucleotides. Each transfer RNA molecule recognizes only one amino acid, which becomes
This is
bonded
much
to
more
the top of the
diagrammatic
transfer
and
RNA
slow
molecule.
things down a little bit.
Located on the
Here we
bottom
go.
of the transfer
So this is-
RNA molecule are 3 nitrogen bases called an anticodon.
All right, so if you look at this is kind of slow. So if you take the tRNA, up on this end is going to be one of the 20 amino acids, right? And it corresponds to the anticodon here, and that anticodon is spelled out. This is fixed. These are us floating around there. And then what they're waiting for is the ribosome to expose its mate, which is basically the codon. What would the codon be for this? This is a U, by the way. A-U-G. So if you have an exposed message like that on the mRNA, this guy is fair game to bind to it. And when it does, that amino acid just gets transferred. And I'll show you that.
That pair up with messenger RNA codons during translation. As translation begins, the first codon of the messenger
Recognize
RNA
that
strand
guy?
attaches to a
Start.
ribosome. Then, transfer RNA molecules, each carrying a specific amino acid, approach the ribosome. When the transfer RNA anticodon pairs with the messenger RNA codon, the two molecules join. Often, the first codon on messenger RNA is AUG, which codes for the amino acid methionine. AUG signals the start of protein synthesis. The messenger RNA then slides along the ribosome to the next codon, where a new transfer RNA molecule carrying an amino acid will pair with the messenger RNA codon. The two adjoining amino acids then become joined by a peptide bond, and the first transfer RNA molecule is released by the messenger RNA. As the process continues, a chain of amino acids is formed until the ribosome reaches a stop codon on the messenger RNA strand.
Make sense? Okay, this one really does put it
That
together.
makes a lot
Yep.
of sense.
Yep. The first one I just wanted to show you the world. All right. Go ahead.
When it's A to T,
It's not.
when it's A to T instead of A to U, is that in the making of like DNA?
You will see no T's in RNA. So
So if it says RNA, just don't use the T.
Yep, there's no T's.
Okay.
Okay? So the only time you'll see T's is in DNA.
Okay.
And that's one easy way of chemically deciphering which is which. Okay? And that, okay. So let me just recap that again. Hold on, Lauren. I'll go through. Okay, so just see if this makes sense, a little more sense now. We go through the steps. Okay, so here we go. mRNA attaches to the ribosome, right? The DNA with the corresponding anticodon attached, recognizes that codon. The amino acid that is on it it's on chain, starts the chain. The first one would be the start signal, and everything afterwards just gets tagged to it, attached to it. Next, it slides along. Next TNA binds to its corresponding anticodon, continues along. The amino acids are formed by a peptide bond. There's enzymes actually that do that too. Obviously, we're not worried about those guys. And this continues all the way along the chain from start to stop until the entire gene is coded for, at which hits a stop, the ribosome falls apart. Got a polypeptide protein. That's translation. Okay? Taking the mRNA, converting it into a polypeptide. All right.
So technically, if the sequence never really ended, like for a long time, you have a really long polypeptide.
Yeah.
Is there a certain amount?
Yeah.
Where it's like
Some proteins, particularly enzymes, because they're so complex, way back when they get to a real globular form, they tend to be longer. And some proteins are so. Yeah, depending on the complexity of the protein and the length, the process can take much longer. And obviously, the mRNA is longer because the protein's going to be longer, and the strain of the DNA is going to be longer. So yeah, it's all kind of correlates. Okay, shoot.
How do they determine like which amino acid they're gonna make? Like
it's gonna need glycine or glutamine.